Okay, today we are going to discuss Z transform. First one we review for analog signals. We have a Fourier transform and we have a Laplace transform. We didn't discuss Fourier transform in this class, but we did start from definition of Fourier transform. We introduced Laplace transform. The reason for we introduced Laplace transform is because for some signals, Fourier transform, the Fourier transform does not exist. So we want to make this one more signals to convert. So that's why this, for example, f omega equals this ft times e to the negative j omega t dt. What we do here is s equals this ft times e to the negative st dt. We just revise this term into a complex s instead of omega. Then we have a Laplace transform. And for this is the last two chapters. And the next one is for discrete signals. We are going to have a discrete Fourier transform. Counterpart of this Fourier transform is called discrete Fourier transform. But again, good news, maybe we don't discuss this. So for completeness, at least here, we don't do that. And instead we do Z transform. So what is the discrete Fourier transform? Again, I need to list the definition. So this one will be equal to x e to the j omega equals the sum. We cannot do integration, right? Because this is discrete. We don't have an integration anymore. This one is n from negative infinity to positive infinity, and xn, the input, the signal sequence, and times e to the j omega n. If you look at this, compare this one to this, this is very similar. This is time t, this is times n. Time n, this is negative j omega dt integration. Okay, this is just summation with respect to time n. So it's almost the same. And this is a continuous signal, this is discrete signal, discrete sequence, that's all. Again, we don't discuss how to do this and everything. The same thing for this one, Z transform, is we want to make more sequence to converge in this way. And what we do is we use this xn and we multiply this one by r to the negative n. So this looks like an exponential, decreasing exponential. So make the signals more easily convert to the sum. But we are going to combine this term and this term together as in from a Fourier transform to Laplace transform. So the formula is equals the sum negative infinity to positive infinity xn and times r to the negative n e to the negative j omega n, like this. Instead I use this xn, I use xn times r to the negative n. But this is definition, but I don't want to do this first. When we calculate this, I want to do this first. Just like in Laplace transform. So this part will be r e to the j omega to the n. So this one will be xn, then the sum equals like this. Now look at this term. This term is a complex number in polar system, right? So I can write this as z equals r e to the negative j omega. So that's it. So I don't write this long form, I just replace it with a z. Very simple. So that's why, right? So this one will be equal to sigma xn and z to the negative n. That's all. As easy as this. Questions on that? So I will remove everything here, and list here. So this one will be xn times z to the negative n. This one, I'll just copy it here to you. Questions? Recall that z equals r e to the j omega n, j omega. If r equals 1, the z transform, this part will be equal to this one. If r equal to 1, this one is gone. Then this z will be equal to this one. So z will be equal to this one. That means discrete Fourier transform is a special case of a z transform. Whereas this, how is it special? Because this one, if r equals 1, then z transform is discrete Fourier transform. Or we can see z transform is more general than this one. Here r only equals 1, but this r can be anything. Can be greater than 1, can be smaller than 1, can be equal to 1. When it is equal to 1, that is a discrete Fourier transform. Any questions on that? Good? Okay, now can we do exercise? Alright, let's try. Remove this. I'll be right here. Example 1. Use a two-sided or bilateral z transform. Two-sided or bilateral. Just like a two-sided Laplace transform means from negative infinity to positive infinity. Right? One-sided or unilateral means from 0 to infinity. We don't care about the negative. Right? So, okay, let's look at this. Xn equals un plus 1 minus un minus 2. I'll give you this signal. What is the z transform? Definition is here. Xn is given, so you just calculate this. Who wants to try first? I'll give you a hint. Okay, better is we draw this signal first. Right? We know how to draw signals at the first chapter. Right? Okay, we draw this signal first to give us a better vision what this signal is. Right? So how we draw this un minus 1 minus un minus 2. Can you draw this? Draw this signal. Plot this signal. What is un minus un plus 1? Start from where? From 1 or from negative 1? From negative 1, right? So from negative 1, this is 0. From negative 1, so negative 1, 0, all the way to the right, right? Yes? So that is un plus 1. How about un minus 2? Start at 2, okay? So this is 0, 1, 2. So that will be this one, and so on. Now they subtract. What do we have? How many non-zero values do we have?
1, 1, 4.
3, right? This is 3?
Say non-zero.
Non-zero value. How many non-zero values here? Huh?
3.
3?
3.
Everybody look at this. How many? Is that 3? Yes or no?
What would it be 3?
Un plus 1 equals start from here, 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 all the way to the right.
-1.
Un minus 2 start from 2, right? 2, 3, all the way to the right. And we subtract these 2. How many non-zero values? 2. Huh? I want somebody at the back.
I think, I'll say 2.
You think 2?
4.
4. There's 1 reserved. How many? How about you? 2. 2 also? 2 or 3? 2.
You said how many non-zero?
How many non-zero values?
So,
3.
0? I don't think it's any non-zero. 3.
3 non-zero values, right? The first one is at when time equals to -1. The second non-zero is when time equal to 0. The next non-zero is when time equal to 1. Any questions on this? This, subtract this, alright? So this is gone, everything is gone, so we have only these 3 left. Alright? This is n, this is 1. Alright? The z transform of this equal to the sum of all of them from negative infinity to positive infinity. Looks like scary, right? But how many non-zeros do we need to calculate?
3.
Only 3. So I don't need this, I just plus 3 terms. 1, 2, 3, that's all. Okay, now we start from the first non-zero term, which is when n equal to -1. So n equals -1, that means x -1 here. This is n. Then times what?
0.
Look at the definition for z transform. X n equals -1 times what? Times z to the negative n, right? Yes? Okay, z to the negative n. What is n?
-1.
-1. Right? That's the first non-zero value. Right? Then plus, what's next?
X to the 0.
X, 0, good. Then z to the negative 0, right? Then, do we have other terms? Yes. What's next?
1.
x1 times z to the negative 1. What is x -1?
1.
1. What is x 0?
0. No, 1.
1, right? What is x1? 1.
That's referring to the singles.
Yeah, from here, this is the only 3 non-zero values. All others, how about the negative as x -2?
0.
Negative positive 100? 0. We have only these 3 non-negative values, which all of them are equal to 1. Right? So what is this? Z, right? I will remove this. So this one equals to what? Z? Good? Yes or no?
Yeah.
Yes, okay. What's next one? is 1? Is the second term equal to 1?
So it's equal to x.
This one equal to 1. How about z to negative 0?
That's 1. 1 times 1.
That is 1. 1 times 1 equals 1. Yes, that's good, right? Alright. Then what's the next one?
BZ. Well,
This is 1. This is z to negative 1. Means 1 over z, right? Are we done? Kinda, right?
Yeah.
Yep, we done, right? So that's z plus 1 plus z to the negative 1. That's it. That's the z transform. But we still need to consider the, what is that? The region or the area that make this exist. How about z equals 0? Okay, let me ask this. What is x0? What's this? We know this z transform, right? Eh? What is x0? That is capital X. That means the z transform. Means when z equal to 0. What is x0? This one equals 0. This one equals 1. This one equals
0. Undefined.
undefined. Means infinity, right? So this one does not exist. We cannot calculate this. How about x infinity?
well,
This one equals infinity. Again, undefined. This one equals 1. This one equals to
basically
0, right?
Yeah.
Right? So still equals infinity. Then this one still does not exist. So we need to consider what is the term in Laplace transform? 3 letters. Abbreviation for
simple fraction expansion.
region
Region of convergence.
of convergence. ROC, right? Because not all z make this converge. So we need to state the region of convergence. So in this one here, what is ROC? The region of convergence is every z except 0 and infinity. For example, how about z equals 1? It's good? It's good, right? Equals 3. How about 1 and z equals 10? It's good? Yeah, that's good. That's 11 and 0.1, right? How about z equals negative 5? Okay, still good. So every z except z cannot be equal to 0, z cannot be equal to infinity. That is the region of convergence.
What about negative infinity?
Infinity, okay, good question. Negative infinity equals positive infinity. Yes or no? Yeah, so negative infinity, positive infinity. We do not need, you can't write, but almost the same, right? Negative infinity is that way, positive infinity is that way. They meet somewhere. Kind of, right? That is long story. Right? So we don't discuss this math. Okay. Any question on this? So we need to state the region of convergence. Right? That's easy, right? Can you do it? The definition is here. I will give you this sequence, then you can calculate this. But use the mathematical techniques we learned all before, from elementary to middle school to everywhere. Alright, so now we have another one that you to try. Let me erase all this on top. And I will copy this formula for you on the top. Okay? Xz equals the sum of negative infinity to positive infinity xn z to negative n. Yes, right? Right. Now we go. Now is example 1, example 2. This is called one-sided or unilateral. One-sided or unilateral. Means we only need to go to one side. Xn equals Un. Oh, that's easy. Now you calculate the xz. What is this? We use the formulas, right? I'll let you try first. Not that hard. Don't be scared. You try first, then let's see. If you start somewhere, then let's see where you start. Okay, let's try together. This one will be equal to, I copy this. But what is xn? Un. Un means like this. So we start from 0 and all the way to the right,
N equals 0 to infinity.
Yes, from 0 to infinity. We don't need to calculate, worry about negative time. So that's why it's called one-sided. So this one here, n equal to 0 to infinity, because all the negative times the corresponding signal equal to 0. So we don't need to do that. So that's why it's called one-sided, only to one side. We don't need to do two sides. Okay, so here, xn, once if the n equal to 0 to infinity, what is xn? For example, what is x1? 1. What is x2? What is x100?
1.
All equal to 1, right? Like this. Okay, so 1 means I don't need to write. 1 times. What's the next? Z to the negative n. That's all. Because xn equal to 1. Make sense? Okay, now looks this simple, right? But you cannot leave this like to me like this. You need to calculate the sum. Right. Let's see. What is the first term? When n equal to 1, what is it? 1. Okay. Sorry, when n equal to 0, what's the first term? 1. Okay. Z to the negative 1 is here. 0 to the negative 1 equals 1. What is the second term?
1.
When second term is n equal to 1. Z to the negative 1. Right? So that will be Z to the negative 1, right? Then what's the next term?
Z to the negative.
Z to the negative 2. Right? And so on, all the way to infinity. Oh, you don't stop at this point. You need to give me the sum. What sequence is this? This looks like sequence, right? Right? Geometric sequence. It's good. How to calculate the sum of a geometric sequence? This is again a long time ago. Right? As high school, middle school. So what is how to calculate the sequence? This is the geometric sequence. This one will be equals the first term divided by 1 minus. This reminder anybody?
No, honestly not.
Divided by the ratio between the terms. This one or this, what is this? This one or this equals what? Each term is multiplied by z to negative 1, right? So this one equals 1, this one multiplied negative 1, then this one is this multiplied z to negative 1, and so on. So the ratio between the adjacent term is z to the negative 1. So 1 minus this, z to the negative 1. I list the sum for the terms, and because you are going to use this in your homework or in the test, so you need to know that. For the sequence, if the sequence is a first term, the second term is a times q quotient. The next term is a geometric sequence. What's the next term? Q to the square, right? So you can see the quotient, the ratio between adjacent is this one over this equals q. This one over this equals q. What's the next term? To the 3 and so on. If we have an infinite term, then the sum will be equal to the first term, this is the first term, divided by 1 minus the ratio. What is the ratio? Q, right? Divided by Q, that's it. But in the homework, I may give you a little bit more difficult than this one. This one has infinite term, so it's easier. If I give you finite term, for example, only 10 terms, that is more difficult to calculate. For n terms, let's see what is it. So it will be a, so suppose S equals a plus aq plus aq2 plus aq n minus 1, right? Capital N minus 1. This is n terms, right? First term, second term, third term, and n minus 1, so that's n term. Need a response, yes or no? This is n term geometric sequence. The first one equals a, the second one is aq, the next one is aq squared, and the last one is aq n minus 1. Yeah? Yes or no? I want to calculate the sum, so add all this together. I assume that equals s. So I want to calculate f. What is s? Okay, how to do this? There's a formula, but if you forget, now that's easy to derive. What we do is you calculate q times f. What is a times q? That is aq. Okay, I put it here. What is a q times the second term? aq squared. Okay, I put it here. aq squared, and so on. This one aq n minus 1, but this one multiply q, that gives us aq to the n, right? This is the first term, second term, and this is the nth term. Make sense? Now, what I do is I just subtract. This one, the whole equation minus the second equation. The left-hand side is s minus qs, so that is 1 minus q times s. Yeah? Yes, okay. Second term, now that is the beauty of this method. A minus nothing, we don't have a corresponding a term, so that's a here. This term minus this term is gone, right? This term and this term cancel. This term cancel. This term cancel. How about this term? We cannot cancel. This term is here. So this one minus this will a minus aq to the n.
So what operation did we just do right there? What was that?
We try to find the sum of n terms. Give you a sequence. This is supposed to be in, again, high school. I just give you a review. This one is for infinite term, how to calculate the sum. How to find the finite term, for example, n term. What is the sum for geometric sequence? We are deriving the formulas here. So you can see, this is f, what we want. So that's S equals A times 1 minus Q to the N over 1 minus Q. Right? So that's the formula. So I write here. You read this, right? Alright, so this sum will be equal to A times 1 minus Q to the N over 1 minus Q. Alright? Memorize all these both formulas. You're going to use this. Nothing fancy, nothing new here. We don't need to discuss this in this one. Okay, now, so this term add up together equals this. Yes or no? Yes, right? Why is 1 here? Somebody add back. What's this one? Good, first term. This one is here. Why is 1 here? What is this one? First term? No, that's not first term. This is 1. No matter what your first term, second term is, this is always 1 here. So this one is 1. This one is the first term. What is this z to the negative 1? That is the ratio between adjacent terms. So Q here. This one over this equals Q. This one over this equals Q. Geometric sequence means all the ratios must be the same. Alright, so this one here. Okay, that's it. That's the final result. The Z transform for UN. Can you tell me what is the region of convergence?
For whatever.
Alright, that's not easy to see, right? Okay, let's make this simplify. I multiply by z on the top and the bottom. That's okay, right? So on the top that will be z. On the bottom that will be z minus 1. Yes? I multiply top and bottom both by a z. So that gives us a z on the top, z minus 1 on the bottom. So now can you tell me what is the region of convergence?
Z can't equal 1.
Z cannot be equal to 1. If z equals 1, then this one equals infinity, so you cannot do that. The sum equals infinity, then we cannot do that. Is that all? Z can only not be equal to 1?
I think so.
Can z equal to 0? I remember in the first one, z cannot be equal to 0. Can z equal to 0 in this case?
Yeah.
Yes, right?
Z can't be infinity.
Can z equal to infinity?
No.
Huh?
No.
No?
Well, it'll be 0.
Infinity over
Never mind.
infinity
It's 1.
equal to 1, right? That's a limit. We learned limit in Cal 1, okay? So you know that prerequisite for this class is Cal 2. So, well, z equals 0, no problem. Z equals infinity, good. Only thing we cannot, z cannot be equal to 1. So that is the region for convergence. Z cannot be equal to 1. Okay, now that is, I want you to be careful. In our textbook, in our lecture notes, in our class, in our homework, everything, we prefer to use this term. And if you read some other textbook, they may want to use this term. We know these are equal, but we don't like this term. That's the reason I will let you know later time. But keep in mind, we are going to use this term. Let me give you a little quiz. What is the Laplace transform for unit step function?
1 over S.
1 over S, perfect. What is the Z transform for unit step function?
1 over Z.
1 over Z?
No, it's just 1.
Huh?
Z. Or Z to the N.
It is here.
1 over
Okay, so see, that's a little bit different, right? The Laplace transform for the continuous time step function is 1 over s. That is good. But this one equals 1 over 1 minus z. We always have 1 here. This one is always. This is always here. Okay. We discussed before the complex S-plane. You still have, can still remember that, right? The region of convergence for Laplace transform is an area that half plane, right? Can only be to the right or to the left or something to the left or something. So it must be a half plane. So how about the region of convergence for this one? Remember this one we use Z, means a polar system, complex numbers. So we instead of use half planes or something, we are going to use circles. Because Z is represented by Z equals R times e to the negative omega. So this one is polar. So we are going to use the circles. Everybody write it? You need to use this. If you don't write here, then you check online. The region of convergence, we are going to complex Z plane. So this is Z here. This is like this Z plane. And we are going to use, instead of like Laplace transform, we use this part, that part, half planes. We are going to use the circles. So like this, or something. So the region of convergence can only be a circle. For example, this one, Z cannot be equal to 0. That means this one equals 0, right? So cannot include the origin. Z cannot be equal to infinity. That means infinity. So the whole plane is in the region of convergence except the origin for this part. Make sense? For this one, Z cannot be equal to 1. If Z equal to 1, for example here, that means this is a unit circle. Right? So the region of convergence for this one will be everywhere inside or outside, but cannot be on the unit circle. Right? That's the region of convergence. The region of convergence can be outside, like this. Can be inside, like this, or can be a ring, like here, inside this, and outside this. How about this one? The region of convergence will be like this. Here, inside this, and outside this. Well, that's not going to work. All the region of convergence must be connected. This one, here, this one. These two are not connected. This one is not connected. So the region of convergence is either inside the circle, or outside the circle, or a ring. Okay? And there are some other properties of a region of convergence. Then you can. It's on slide 87. Okay. Any questions? Can we do more exercise for Z transform? It's also help you with the Laplace transform. Okay, again, I just leave this definition here. And you don't look at your notes, you only calculate this. First one, example 3, xn equals a to the n u. We discussed UN before, the second example, but now there's the exponential AN times UN. What is the Z transform? Everybody start. Definition is on the top. That is you should bring to the test on the cheat sheet. Anyone try?
Is it a to the n times 1 over n minus c negative 1?
Okay, yes, I think that is correct. All right, let's do together. All right? Anyone get similar result? 1 over 1 minus a to the a times z to the negative 1. All right? All right, let's see. Sum n equal to this two-sided or one-sided?
Unilateral. One side.
One-sided, right? Because of UN. So from 0 to infinity, a n z to the negative n, right? The best practice for you to here follow this and to think actively, not just copy this. Everything is in the slide, so you don't need to copy this. Right? If you think this is the question you ask me, that help you more than you just write everything on a piece of paper, then you may don't have time to read after the class. Right. So this times this, what we do is we are going to combine these two terms. This one will be n equals 0 to infinity, combine these two terms. So that will be a over z, then to the n. Right? Right, so now let's see, what is the first term? N equal to 0. What's the first term? 1? Yes or no? Again, the purpose in the class is help you to solve the problems. Don't write. So the first term is 1, right? When n equals 0, this equals something to the 0 equals 1, right? Okay. Then what's the second term? When n equals 1? A over z. Okay. Now, what's the next term?
A over z squared.
Okay, over z squared. Perfect. Then we have infinite terms. Alright, that is the sum of infinite terms. This is geometric sequence, right? What's the sum equals? 1 on the top. What is this 1 here? First term over 1. This one is 1, right? Not first term. Minus a over z. Right? A over z or says az to the negative 1. I think that's what you said, right? 1 over 1 minus a z to the negative 1. A over z means a times z to the negative 1. Okay, so now let's see what we need to think next. The radial convergence, right? the region of convergence, look at this one. We need to add all this together. If this A over Z equals 1, 1 plus 1 plus 1 plus 1 plus 1, can we do that?
Yes.
What is it? Infinity, right? That means diverge. We cannot do that. Right? How about if A is greater than Z? That means Z is greater than A. Z is less than A. For example, this one is greater than A is greater than this. For example, A over Z equals 2. That means 1 plus 2 plus 4 plus 8 plus 16 plus 32 and plus so on. Can we do that? Infinity, okay? We cannot. This formula only works when Q is less than 1. So in this formula, again, we didn't mention this, so now you go back to your notes. For the formula for the infinite terms, the Q must be less than 1 for the formula to convert. Right? So here, that means A over Z must be less than 1. Or Z is greater than A. Right? Okay, now keep in mind the region of convergence must be a circle or something. So actually this greater than absolute value of this. We don't care the angles, we only care the radius. Right? So the region of convergence for this will be, your A is here, suppose we know the A, right? Suppose A is here, then what is the region of convergence? We need to draw a circle centered at origin. The radius equals the absolute value of A. Then where is the region of convergence? Can only be inside or outside. So in this case, outside, because Z must be greater than A, so it must be outside. So the region of convergence is this one. If you draw this, this is here. Make sense? It's good. So we need to calculate the Laplace Z transform and also the region of convergence. Eh? How about A equals 1? A equals 1, what is this? Unit step. We already did this, right? Second example. So A equals 1. Okay, now A equals 1. Is that what we said? 1 over 1 minus Z to negative 1? Yes, that's a special case. In Laplace counterpart, we know ut give us 1 over s. That is like un give us 1 over, what does un give us? 1 over, test the of this. 1 minus z to negative 1, right? Laplace z. And if this one is e to the negative at, always a plus e to the at, this one will be changed to s minus a, right? And if this one a to the n, this one will change into a here. So now you know at the beginning we discussed how to do inverse Laplace transform. You know this, the importance of this. All right? Again, memorize this. Okay, any other questions? We still have several examples, but we are going to continue next time. Okay, thank you. That's it.